Okay, so this time we're gonna give you guys numbers. I said if theta equals 30, m1 is 5 kilograms, and m2 is 1 kilogram. I wanted to know the acceleration and the force of tension. So A equals what? Force of tension equals what? Okay, and I want to know which direction the system moves. So, assigning our x direction. And we said we were arbitrarily going to call this direction negative and this direction positive. Okay, and our y-axis. And then I'm going to start identifying forces. So we talked about this before. We have normal force. We have FGY. Drawing our gravitational force for that one. This is our FG1. This was FG1X. And that was our FG1Y. Okay. And then we have our force of tension on 2 pulling up, and we have our force of gravity on 2 pulling down, FG2. Okay, so I'm going to choose to go with the sum forces on the system, and that would be our FG2 minus FG1X equals mass of the system times acceleration in the x direction. Okay, and no matter which direction they ask you for these, if they ask you for force of tension in a part A of a problem and then acceleration in part B, you need to always pick which part is easiest to solve for, even if they don't ask you for acceleration. You're going to have this before you can solve for force of tension. So don't be tripped up if they reverse which order they ask for something in, or if they never even ask for that. You still have to have the acceleration. So always go for that one first. Okay, so we have FG2, which was m2g minus m1g sine theta equaled m1 plus m2 times acceleration in the x direction. So our acceleration we said was m2g minus m1g sine theta over m1 plus m2. Okay, and if we solve through for that, we have m2 is 1 kilogram, g is 9.8 meters per second squared, m1 was 5 kilograms, and our theta was 30 degrees, all over the combined mass of 6 kilograms. It works out to have an acceleration of 2.45 meters per second squared. And it's a negative. So if the acceleration is a negative, we assign this direction as positive, so the system's actually going to slide down the ramp. This pulley system with the mass hanging here doesn't force it to move downward, it's just going to slow down the object, or the mass 1 sliding down the ramp. It doesn't stop it, it doesn't reverse its direction, it merely slows it down in this case. So you could say negative 2.45 meters per second squared, but if you're going to answer it on an AP test, it's always best if, even though you've shown how you assign direction up here, we all know how it is when they're grading things, or what if I'm grading things late at night and it's midnight and I'm not paying that close of attention. 2.45 meters per second squared down the ramp. Okay, if you add that notation on there, it keeps us from marking it off. You don't want to lose a point, or worse, for not specifying which direction. Because what if you didn't draw on here which direction is positive and which direction is negative? What if you just assume that they know that you're taking that to be positive? They won't necessarily give you the points. So you have to specify that it's going down the ramp. Okay. I'll go ahead and take this part off. So we know the fact that the acceleration was 2.45 meters per second squared down the ramp. Or based on our notation, negative 2.45 meters per second squared. And we had the equation that we solved through earlier for force of tension, but we'll go ahead and just look at it again just to be safe. Some forces on object 1. We have force of tension, we took that direction to be positive, so Ft minus Fg1x equals m1 times acceleration in the x direction. Okay. When I plug this through, let's just rearrange first. Force of tension equals Fg1x plus m1 acceleration. Okay, Fg1x and 1g sine theta plus m1 acceleration in the x direction. When I plug in for this, I need to make sure that I keep my signage. Okay, I'm still calling this direction positive when I summed my forces. So if I'm calling this direction positive when I sum my forces, I had better keep my negative on the acceleration, or bad things are going to happen. Okay, 5 kilograms, 0.8, sine of 30, plus 5 kilograms, and our acceleration was a negative 2.45 meters per second squared. If we total that out, our force of tension works out to be 12.25 newtons. Okay, and this was looking at it from the perspective of mass 1. Okay. If we have time on a free response, you should always double check it by looking at it from the perspective of the other mass. Is this mass experiencing the same force of tension on the rope here as the force of tension on the rope over here? If it's not, then you've done something wrong someplace in the problem as you went through and solved for things. Okay, so let's take a look at it from the perspective of mass 2. Okay, so some forces on mass 2, we have Fg2, still the positive direction, minus Ft equals m2 acceleration in the x direction. Okay, so we'll rearrange, we get force of tension equals Fg2 minus m2 acceleration in the x direction, m2g minus m2 acceleration in the x direction. So force of tension equals 1 kilogram times our 9.8 meters per second squared minus the 1 kilogram times, don't forget the signage, negative 2.45 meters per second squared. Okay, and then our force of tension should still work out to be 12.25 newtons. Okay, and that is from summing forces on mass 2. Okay, I'm gonna assign a practice problem. I'll put one up on the Google Classroom with this, and I'm gonna have you guys solve through that. I will add one that includes friction tomorrow. Once you've solved those that have friction, the only thing that's left for you guys, let's see, a double inclined plane with a pulley at the top, boxes with ropes in between on flat surfaces, which is a cakewalk after this, and boxes that are stacked with different coefficients of friction between the boxes and the bottom box and the floor. So once we've conquered that, you are completely done with forces and you're ready for the test on Friday. Okay.